Hello, everyone. I hope you can hear me. I was trying to think of some good topics that we've been working on in my group, and then some good kind of broader climate topics that came out of the work on the IPCC Ocean, Cryosphere, and Sea Level Change chapter. So that's what I'm going to talk about today. And I think if you have one idea to take away, there's something called the recalcitrant mode of climate adjustment, which is what I'm going to try and highlight. The recalcitrant mode really has to do with changes to the deep water, but it has impacts for the climate system in terms of climate sensitivity, thermosteric sea level rise, and it also links, interestingly, to what's going on at the surface in a way that can be monitored. So I'll tell you what I'm going to say up front. Here are the conclusions. So the ocean, particularly the deep ocean, is part of the slowly responding or recalcitrant parts of the Earth. We're going to talk about the energy budget, thermosteric sea level rise, and carbon budget, and a kind of relatively new concept in climate science called the zero emissions commitment, which importantly relies on the ocean uptake of both heat and carbon. One of the key tools I'm going to use is emulators. So an emulator is not quite a full climate model, it's a model of a climate model. And so an emulator is cheap and fast and just answers a few questions. And you'll see as we go along how that allows us to access interesting new parts of the science that we can't get without a tool like that. So the basic starting point for both the emulator formulation, but also climate models, is the energy balance of the Earth. So the sunlight comes in, and then the thermal radiation goes out, as well as the reflected sunlight. And if everything were stationary, the outgoing would be equal to the incoming. But as we know, one of the important effects of global warming is that when you change the greenhouse gases in the atmosphere, the outgoing gets trapped, and so you actually accumulate energy. Just a few watts per square meter over the Earth, but most of that energy actually ends up in the ocean. And so in early attempts to figure out how this process might work, the group at GFDL did a couple of experiments where they changed the CO2 concentration, anticipating future conditions, and then they reduced the CO2 concentration back to pre-industrial states. So that's what's shown here on the left. The 4 red dives are when they reduced the CO2 concentration back. And what they were rather aggravated by was when they did this in a couple GCMs, so atmosphere and ocean, the system doesn't go back to pre-industrial. It drops to a slowly increasing remnant, which they called a recalcitrant response. And that recalcitrant response is really because the deep ocean is warming up under global warming, and it's incompletely equilibrated over these, decade or century length runs. And so this first paper, their real complaint was, well, this makes it really hard to spin up our climate models. How are we going to get to a state where we can study climate? A very closely related idea, this is a figure from the IPCC chapter, is the idea that we can monitor the energy inventory of the Earth. And most of it, as I said, ends up in the ocean. So you can see on the left, this is the global energy inventory. The biggest changes are seen in the surface ocean, but pretty substantial changes in the deep and abyssal oceans as well. And then only a tiny fraction of the energy actually goes towards melting ice or warming up the land. And a teeny tiny fraction is actually warming up the atmosphere, which is funny to think about because the atmospheric warming where we live is what we frequently think of as global warming, but actually from an energy perspective, it's mostly an oceanic change. And when warmer water is bigger, it's more voluminous per unit mass, has a lower density than colder water. So there's an expansion effect that goes along with that. And so on the right, in the same colors of ocean, we're seeing the thermosteric expansion that goes along with that ocean warming. And then on this side, you actually can see the land ice from glaciers, Greenland, and Antarctica, because when they melt, they add more mass to the oceans, which also leads to sea level rise. And the important distinction on this side is if you observe each one of those systems independently and figure out what its sea level contribution should be, the total adds up to what we observe from both tides and altimeters. And so there's no missing sources of sea level in the system. And when we look to the future, those are, I should have said, those are observations that I was just showing. When we look to the future, the story continues in much the same way, whether we're under a high emission scenario or a low emission scenario. So here, the little pink pills each indicate 1 centimeter of sea level rise from thermosteric ocean warming expansion. And so as we go forward to 2050 and then on to 2100, you can see that the pink pills are about half the story in all of the cases and are about half the story at present as well. The melting of the ice sheets starts to be a much larger contributor in 2100 than it is at present, or in recent observations. And so the last topic of this kind of general climate introduction that I wanted to talk about was the zero emissions commitment. And this is really something that arises in emissions forced Earth system models. I was careful when I talked about the Held paper to point out that the way they were forcing global warming was with changing the CO2 concentration in the atmosphere. And of course, humans are changing the CO2 concentration in the atmosphere, but we're not changing it with a dial on CO2 concentration. We're changing it by emitting a certain amount of carbon or carbon dioxide each year, as well as methane and other greenhouse gases that can be built into this system without too much fuss. And then the carbon cycle is what's responsible for removing it. And so the carbon cycle removals are, about a third goes to the ocean, about a third remains in the atmosphere, and about a third is taken up by the land surface terrestrial carbon cycle. And so Earth system models actually model the carbon cycle as well as the physical processes. And so you kind of ask a different question, the question of what happens if you are emitting, and then all of a sudden you stop? What happens after you stop? And this is quite different from what happens if you return the carbon dioxide concentration to pre-industrial conditions, because the concentration remains at whatever it was when you stopped. You're just not changing it anymore through emissions. And so you can imagine that the temperature would go up and then the temperature kind of levels off, plus or minus some growing uncertainty. And that uncertainty is what's called the zero emissions commitment. But as we talked about with the recalcitrant mode, the sea level rise and mean ocean temperature at all depths will continue to rise as even after this period, as the deeper ocean warms up and warms up. And you really can see that this response over here is complicated because some parts of the energy cycle respond fast, the clouds, the atmospheric temperature, while others are slow, the carbon cycle, the deep ocean, and the Greenland and Antarctic ice sheets. And so when we think about the deep ocean contribution here, it really has two roles to play. One is taking up some of the CO2 from the atmosphere. That's what this top graph is schematizing. And it's also taking up energy or heat uptake by the ocean. And both of those, once you stop the emissions, we expect them both to decrease, but we don't know which one decreases faster. And the decreasing faster of one or the other is what really sets the bounds of this envelope of the ZEC. So studying both the carbon cycle and the energy cycle in the ocean and the transfers of both to the deep ocean and any distinctions between the two is really a key part of this ZEC science. Now I wanted to switch over to emulators to try and give you a little handle about that and see how that works. So an emulator is really, it could just be something like a neural net that just emulates the output of a climate model, but often it's more illuminating to build an emulator that's really like a physical model, so a toy model, but then one that is tuned to be quantitatively accurate in comparison to climate models. And so if you want to think of what a simple system of the exchanges between the surface ocean and the deep ocean might be, this paper by Anand Gnanadesakan is a great example, where you have a picnic line, you have an AMOC, a northern sinking, you have a southern ocean that has a residual circulation and an Ekman transport that's also exchanging surface waters with deep waters, either through the upper branch into Antarctic intermediate water or the lower branch into Antarctic bottom water. And this is the kind of process that you'd like to simulate if you want to get a handle on the recalcitrant mode. So the student, an undergrad actually of mine, Galen Hall, and I started thinking about how this system works, and we picked up on this long thread of building simple toy models that have a surface energy balance, which is this part. So there's a heat capacity of the surface and a surface temperature change, then a heat capacity of the deep ocean and a deep ocean temperature change. So the surface could equilibrate just by radiating more outward when it gets hot and then experiencing fluxes from the atmosphere or from the top of atmosphere fluxes that are incoming. But you also include an exchange term. And this is very simply just done as a diffusion from the upper layer into the lower layer or vice versa, depending on the relative magnitude of the anomalies in temperature between the surface and deep. This little efficacy factor right here, this epsilon, is a way of saying that maybe if you have an anomaly, you don't diffuse down to the deep layer, but you actually might lose it off to space instead. So whether that number is greater than 1 or less than 1 depends on how much of the energy you send downwards versus how much you exchange with space, is the way to think of it. So this is a simple model. It's just 2 ODEs. I should have said these temperatures are globally uniform, surface and deep. But the problem with this is that none of the parameters in this model are actually observable. So instead, what you have to do is you have to train this model based on its rate of warming in the surface and the deep. And you can think of doing that by just launching off a bunch of CMIP models, and this is a whole ensemble of CMIP models. And if you examine this, there's a fast adjustment timescale, which is mostly the surface adjustment. So that's over just the first few years of the simulation, and then a slow adjustment timescale as the deep ocean catches up. And so you can imagine fitting one of these models as it quickly increases and then slowly increases, like this, where you go downward here as it quickly increases and then maybe a different slope as it slowly increases. And using that, you actually can infer all of the parameters of this model. So we can build this model in such a way that it mimics each of the CMIP models. Well, that's not the only thing you can do, because you can also examine how these parameters vary across different CMIP models with other things you might be able to observe. A really interesting one is the mixed layer depth. And the mixed layer depth is correlated to many of these parameters across the CMIP ensemble. So essentially, models that have excessively deep mixed layer might have an excessively large lambda, and vice versa with shallow. We found that it was really important to distinguish the mixed layer in 3 different regions, which should remind you of the non-Odessican model. The Northern Ocean, the tropical ocean, and the Southern Ocean really have different controls or different correlations with the different parameters of this model. And over here, we're just showing that in a little bit more detail. Here's the Northern Ocean at the top, which largely change, if this is the correlated temperature change, so it's connected to North Atlantic deep water and really AMOC overturning. The tropical ocean is really related to tropical upper ocean temperatures. And then the Southern Ocean has a deep branch and a shallow branch that are correlating with the Antarctic intermediate water and the gyres broadly, but also some impacts on the North Atlantic deep water. And so when you do scatter plots of the different parameters of this model, along with these different mixed layer depths, frequently you find a pretty reasonable proportionality. This vertical bar here shows the observed range of mixed layer depth. So as you can see, most of the models are not within the observed limits. So we use that fact to do something called an emergent constraint, which is where we constrain, that is, slide all the parameter values of those models by moving them toward the observed range of mixed layer depth for each of the different regions. And that gives us a new set of ensembles that are matched, ensemble of emulators that are matched to the CMIP ensemble. But it's like the thought exercise, what could we do if we could fix the climate model so that its mixed layer depth was correct, rather than biased the way that they are? And so you get an emulator set that's kind of like, well, if we could fix the mixed layer depth, and that might be by changing ocean processes, but it also might be by changing atmospheric processes, cloud parameterizations, all of that. And just for a sense of scale, the amount of adjustment we have to do here is about 5 times bigger than what you get from adjusting an ocean mixing process alone, like adding Langmuir turbulence physics or the submesoscale parameterization. So this is a pretty big adjustment to the mixed layer depth. It probably involves multiple parameterizations and resolution effects to get yourself all the way there in a realistic GCM. But in this toy model, we could just do it by just tweaking the parameters in order to push the correlated parameters into this value. And what's interesting about that is when we squeeze that and therefore change these parameters, we can ask what would happen to future uncertainty in things like surface temperature change or sea level rise. And this is a pretty dramatic change in those outcomes. It's about a 20% reduction in the uncertainty of transient climate response. So that's the climate response at the end of a 1% CO2 increase, and about a 45% reduction in effective climate sensitivity, which is sort of the long-term estimate. And this is not a trivial amount. So an economist here estimated that if you could have this uncertainty, it would be worth $10 trillion. So this is a toy model. This is certainly not proof that we have the uncertainty, but you can understand why expressing things in this formulation is helpful for thinking about why we really could do better at surface processes. So before I run out of time, I want to talk just a couple of minutes about this other emulator. And this idea is very similar to the last one. It has a surface temperature and a deep ocean temperature and an exchange between the two. It's based on almost the same equations, but this time we use this system to assimilate observations. So rather than a free-running emulator or a free-running climate model, this is a data assimilating emulator. And so you can see the annual mean surface temperatures are superimposed here in the little gray dots. And in fact, this is a reconstruction of deep ocean heat content, which is from the Zana et al. Reconstruction. And the cool thing is that in this system, you can ask like, so this is an extended Kalman filter framework, if folks are familiar with statistical models. But what this means is you can monitor the changes in the Earth system and see whether your temperatures are getting outside of your envelope of the expected weather. That's this blue envelope for both sides. Or how your climate state. So this is our climate state is tuned to be close to the 30-year mean temperature, but we don't have to wait 15 years to look back in the past to find a 30-year running mean. This is an instantaneous estimate of the climate state. And so you can ask questions like, has the climate crossed the 1.5 degree policy threshold now? No, it hasn't. And but this is a probabilistic model, so it gives a probabilistic answer. But interestingly, last year's weather was so warm and there was sufficient global warming that there was actually a 16% chance that 2023 itself would have been over 1.5 C. We're going to see this year with a big El Nino is off to a good, quite a start. It may be crossing 1.5 C for the annual mean this year for the first time. And so this model has basically the same kind of dynamics as that schematic I showed before. I'm not going to go into the equations. One other thing you can do with this is you can examine like what are the effects of future volcanism. So now we're looking at projections into the future under two different scenarios. And by running this model over and over and sampling from a distribution of potential future volcanism, you don't get an ensemble spread that looks symmetric, cold versus warm, the way you do with GCMs that are run with background volcanism. Instead, you see a long tail toward the cold side because if there's a big volcano, it tends to make the climate colder. You can do the same thing in deep ocean heat content, and you don't see as big of an asymmetry, but there is an asymmetry which has to do with that volcanic impact as well. And I'll just close on noting that these models are fast enough to do this volcano simulation because as two ODEs, they're roughly 1 billion times faster than a regular GCM. And that includes, they give you the probabilistic information you get from running an ensemble of GCMs. And in fact, they also are probabilistic, so they're giving you the full effect of an ensemble. So now we'll go back to the conclusions again. So the ocean, particularly the deep ocean, is really part of the slowly responding or recalcitrant parts of the Earth system. Plays a key role in the energy budget, ocean heat content uptake. The energy uptake is proportional to the thermosteric sea level rise, so you have a different observational constraint through sea level. Plays a key role in Earth's carbon budget as well. There's carbon uptake, which I haven't talked much about except for pointing out the ZEC consequences of that. And then through using emulators, we can mimic what a real full climate model would do, but for much less cost. And so we can do things like explore the sensitivity if we could fix the mixed layer depth within a real climate model even though we don't know how to do that. We don't have the science or capability to run at the resolution where that would come into bear yet. And of course, we can also do other things with emulators like data assimilation and sensitivity analyses to parameter changes that are very hard to do in an ensemble of full GCMs. Thank you very much.
Thank you, Baylor. Up next, we have Isabela. And Isabela, you can go ahead and share your screen. Just to note that we are saving all questions and discussion to the end.
So thank you, Baylor, for that talk. That was really a great high-level sort of introduction and motivation for what I'm going to present today. What I'm going to be doing is actually focusing in on the North Atlantic and talking about pathways for dense waters into the deep North Atlantic, and particularly focusing on some recent lessons we've learned from the OSNAP array, which includes the OOI Erminger moorings. I have many collaborators that helped make all of this possible, and I will be acknowledging them throughout as best I can. So one motivation for really trying to understand the processes by which the deep North Atlantic is ventilated is that we think the North Atlantic plays this really important role in stabilizing the Earth's climate. So if you look at the top panel, I'm showing the column inventory of anthropogenic CO2 in the North Atlantic, and particularly the pathways of kind of intermediate water spreading emerge as this hotspot for anthropogenic CO2 spreading into the deep ocean and storage. Another interesting feature that appears to be associated with this deep water spreading in the North Atlantic is that there is much less of an O2 minimum in the North Atlantic if you compare it with the Pacific, for example, that doesn't have an overturning circulation. But when we look at schematics of the AMOC, or Atlantic Meridional Overturning Circulation, we often see tube diagrams like this, where you have warm, salty water moving northward, and then something happens called deep water formation, and then it all comes back southward. In reality, we know that a lot of deep water formation occurs in the interior of these high latitude seas. But then in order for that to actually move southward and get stored, it needs to make its way into boundary currents that flow around these high latitude basins. And these are some of the motivations that set the OSNAP project in motion. So it started in 2014. It's this vast moored array across the subpolar North Atlantic from Labrador to Greenland and then across all the way to Scotland. And like I said, one of the driving questions is understanding this connection between the deep water formation and the actual overturning. So I'll be focusing on the sort of formation and then export southward part of that. Susan Lozier is a lead PI on this huge project, which is also an international collaboration. So a lot of work goes into making these observations possible. Just to go through these tubes again a little bit here, the red tubes are the warm and salty Atlantic water, and the light blue is the cold and fresh waters coming down from the Arctic. And then finally, the dark blue is the deep water. I'm not going to be talking about these overflow waters that are formed in the Nordic seas and come into the subpolar. Those are actually the focus of my grad student Hiroki Nagao's work. So you may hear more from him at the actual meeting. You will hear more on his poster. But I'll be focusing instead on waters that are formed in the Erminger Sea here and in the Labrador Sea. And so the questions I'm going to be targeting are, first, do we have direct ventilation in the boundary currents? So, I spoke about how most of the deep waters form the interior and then needs to get into the boundary current to actually make its way out. Do we have some that's actually formed right in the boundary current, and then you skip over that step of having to move from the interior to the boundary? And then the second question is the one I sort of introduced before. How does that water that's formed by deep convection in the interior actually get into boundary currents? Do we see evidence of that happening? And the results that I'll highlight in this presentation are in the two papers I have listed here and all my collaborators on those papers. are listed on this slide as well. Okay, so the first part, direct boundary current ventilation. So the hypothesis here in the Erminger Sea observations that I've focused on is that when we have down front winds, or sort of winds in the same direction as this approximately geostrophic boundary current, I'll introduce you to the schematic a little bit. Here's Greenland, fresh light water on the shelf, and then saltier water offshore. That's the density gradient. The wind is blowing in the same direction as the boundary current, and so the associated Ekman transport is onshore. So that brings dense water over light water and can cause mixing to great depths through a process called slantwise convection, which forms a low potential vorticity layer. And so we set out to see, first of all, if the level of forcing was consistent with this slantwise convection having a big impact. So here I'm showing the Ekman buoyancy forcing, just the negative part. So just the Ekman buoyancy forcing that causes dense water to go over light water, accumulated over time within the boundary current. So CF4 through CF7 are in the boundary current. And it's much greater onshore where we have higher density gradients. And then it decreases offshore to these green lines over here. And I'm comparing that to the heat loss. So this is a region where we have a lot of heat loss. That's the process that's forming all the deep water in this area. And we can see that at CF5, for example, there is a lot more Ekman buoyancy forcing than heat loss, which is the black line. And in fact, the mean Ekman buoyancy forcing averaged over the boundary current is about 4 times greater than the heat loss. So this gives us a sense that this could be important. And then looking at the mooring observations themselves, I'm here showing a composite event where I combined all of the times when we had that down front wind forcing. And then if you look in at CF5, which is a mooring on the onshore half of the boundary current, you can see that there is an associated drop in potential vorticity at 75 meters, 175 meters, all the way down potentially to about 1,000 meters. So it's a little bit hard to see because the resolution of the moorings are not great. It's hard to get potential vorticity truly, but it's roughly consistent with this what we might expect from the level of forcing. Now, there's a recent study where Fraser Goldsworth took these observations, ran an idealized model, and tried to understand the processes better. And he saw the same thing, and this is really what gave me confidence that the sort of we could go from the consistent with to this is probably happening. So one weekend there's this onshore Ekman transport here near the surface. This is potential vorticity at the top, stratification at the bottom, and then some isopycnals here. You can see that after 3 weeks there's this low PV, very unstratified water right on the onshore side of the boundary current that's mixing water down to great depths. So these symmetric instabilities, slantwise convection, appear to be kicking off and making this connection between the surface and the deep. Okay, but what would be really nice is to actually measure this directly. So try and get a sense for what we care about, the dissolved gases. Are those mixing down? What are the impacts of these processes on the dissolved gases themselves? So to sort of get at this question, starting in summer 2020, this group of PIs listed below, we added oxygen sensors. I led the charge here in the Erminger Sea, and then the rest of these wonderful folks instrumented the whole Labrador Sea. And we added oxygen sensors everywhere where you can see the yellow dots. So it's not quite as dense as the temperature and salinity measurements, but sort of the minimum to try and get a good sense of what's going on with the oxygen and the ventilation here. So, and then our European colleagues at SAMS have added some here in the eastern subpolar North Atlantic, which I won't be talking about. Some very preliminary sneak peek at these data, which I'm really excited about. show that these downfront wind events appear to be associated with saturation spikes in the oxygen down at 1,000 meters. So in red, I'm showing the wind stress that's in the same direction as the current. So these big negative spikes are downfront wind events. And then in blue, I'm showing oxygen saturation at 1,000 meters. So there appears to be a response at 1,000 meters in that oxygen saturation directly following these negative downfront wind events. So this is the first winter, January to May, and then the second winter, January to May. Okay, so moving on to the second part of my talk here. Now I'll be talking about the interaction of convection in the interior of the basin and the western boundary current. So here again are CF5, CF6, which I've introduced before in the boundary current, and then moving offshore, we have M1, and then the OOI mooring in the interior of the Irminger Sea, where deep convection actually occurs. Okay, now this plot is very complicated, so I'm gonna step through it slowly. On the right here, I'm showing a section of salinity with those 4 moorings in these 4 different colors again. And then the black lines are isopycnals, which bracket the water masses that I'll be talking about. Then on the left side, I'm showing temperature and salinity diagrams, and they're color-coded by the same colors that the moorings have on the right. And again, the same isopycnals are also shown in that TS space. And I'm actually going to start here on the bottom left. The size of the circle shows you how much water there is in a particular TS class. And the big thing that jumps out here is that we have this large formation of deep Irminger Sea intermediate water. And that's really similar to Labrador seawater. I'm just calling it Irminger Sea intermediate water because it's very clearly formed in the Irminger Sea. So it has a bit of a different flavor properties. So you see this big mass of this deep Izzy waters formed here offshore at the OOI mooring. And the other moorings show that the TS properties are dragged towards that salinity minimum. So if you look before convection even started, that salinity minimum, first of all, the circles are smaller. That salinity minimum is lighter, and the interior and boundary are not quite as similar. Or rather, there's been a very consistent change from before convection to after convection. The boundary current is clearly feeling the fact that deep convection occurred offshore. This other water mass, the upper Izzy water, is water that's actually formed close to the boundary, and or within it. It's not totally clear, but that has a salinity maximum, and that's the transformation of that Atlantic water, that's warm, salty, red tube water as it makes its way around the basin. So I won't get into it here, but we were able to show in this paper that the water that is formed offshore does make it into the boundary current, and it's really a fast several month time scale. So it's formed in one season, it's exported that same season. And now I want to highlight a similar study, but now in the Labrador Sea, that again shows the utility of directly measuring oxygen. So here, the study led by Janis Kulling. In the bottom panel, I'm showing oxygen in the Labrador Sea interior, so where the deep convection happens. And you can see that there's this big uptick in oxygen around February. And then the top panel is the measurement in the deep western boundary current of the Labrador Sea. And you can see that there's, again, an uptick in oxygen just a month or two after the uptick in the interior. He's also showing spice on here. So the purple colors are colder and fresher, which is a telltale sign of convection, that it cools and brings fresh water downwards. And so you can see that associated sort of in both of the moorings, you see that the water gets colder and fresher in conjunction with that oxygenation. So it really appears to be related to that convectively formed water getting into the boundary current. And then he also went on to do an Argo float analysis where he shows that, where he sort of tracks where the water came from that's showing up in the deep western boundary current. And about half of it comes from the interior and makes its way to the boundary current, but about half is formed near or in the boundary current. So again, he's showing that we need to be paying attention to waters that are formed close to the boundary current or within it, not just these dramatic convective chimneys in the interior of the basin that need to make their way to the boundary current. And then I'm not showing results here, but sort of watch this space for an update from postdoc Una Muller, who's working with Jamie Palter, and assimilating all of the new observations so that these German moorings have had oxygen on them since 2016, I believe. But now that the whole Labrador Sea has been instrumented, there are going to be a lot of exciting results about the ventilation of the deep North Atlantic from these direct oxygen observations. Okay, so I'm going to wrap up a little bit early, I think, with some sort of conclusions and thoughts here. So one big takeaway from me is that understanding the processes by which the deep ocean is ventilated is really essential for understanding how they're going to be affected by climate change. And in particular, it appears that ventilation in or near boundary currents is really significant, and it's not something that's resolved in climate models. Yeah, Baylor's talk actually gave a lot of food for thought of thinking about, how could this potentially be accounted for, given the sort of logistical constraints with climate models. And then finally, I really wanted to highlight the utility of directly observing the dissolved gases. The sequestration of carbon or ventilation of oxygen, it's one of the big reasons that we care about the AMOC in the first place. So now that we can measure these things directly, it's really, I think, informative to measure them directly, not just to gain a better understanding of those processes, but they can also sort of shed light on some of the dynamics sort of in their own right. And then finally, I wanted to highlight this review paper that I recently wrote for the AMOC special edition of the Philosophical Transactions of the Royal Society. It goes over a lot of what I presented today and the sort of broader survey of the literature. So if this topic is of interest, that's, I think, a great resource. And finally, I wanted to acknowledge the wonderful OSNAP group that's making all of these oxygen measurements possible. I listed the PI names, but as we all know, many students and postdocs are doing a lot of the hard work here. I wanted to make sure you saw their faces too. And I will end there. Thank you.
All right, Charlie, go ahead.
Yeah, thanks. And thanks, Baylor and Isabel. I enjoyed both talks, and it was kind of interesting to kind of think about the different scales that they were tackling the problem at. On one hand, you had this very high-level emulator that was representing what Isabella showed are very kind of richly mechanistic processes. And I'm trying to sort of reconcile the two. And maybe I'll pose the question to Baylor and then let Isabella follow up. But what about Isabella's talk, Baylor, makes you perhaps question the things the emulator might not represent well enough, or potentially misrepresent in terms of the deep water pathways in the global ocean?
Yeah, that's a great question. And I think a lot about this, having worked previously on lots of very small scale stuff and really worked hard to figure out whether it counts on the global scale. I guess the short answer is I would like us to get much better at doing that often. I think we like to say that things will be important on the global scale, but then we don't do the extra science to figure out exactly how big of an effect. And the effects will be modest. Like I said, you know, the correction to mixed layer depth was about 5 times what I have figured out how to do from physical processes. So it's a huge set of things that we have to think about. But I think we're not being fair to ourselves and to our, like, you know, the next generation of scientists in choosing problems if we're not trying to estimate where the really big uncertainties are. So I think that's where I'm hoping that this emulator work goes, is that we build a tool that's easy to operate with, and we can kind of do that, make that a more regular occurrence to test those questions. Isabella, I don't know if you want to respond, but I think, I mean, a very big question. One of the things that keeps me away from testing exactly what the AMOC processes are like is that the CMAP ensemble doesn't include any models whose AMOC spuriously shut down. So if there's not a good spread across the models, because all the ones that kind of don't work actually don't end up in that ensemble in the first place. So the little looking we have done into sensitivity shows that often the process level dependence you would like to see turns off the AMOC altogether. And so there are some big problems in figuring out how to do the kind of linearized science I was thinking about in that regard.
Yeah. Thanks, Baylor. I agree overall. Like, you know, one of the next steps for me is trying to quantify, you know, how much. Yes, the boundary current convection is dramatic, and we see it and it's exciting, and we want to understand it. But how much does it contribute to the overall oxygen budget, for example? And I agree that this sort of keep those lines of communication open and really yeah, again, try to answer those questions about what really matters is important. I think understanding how things work in general is super important, because yeah, because then I feel like we should be able to explain the changes that we're seeing. So yeah, and continuing to ground truth with observations as much as possible. I think picking the right thing to compare with is tricky because we operate on such different scales. And yeah, something we have to get better at, something that's not always glamorous and fundable. And, you know, all of us have to justify our existence all the time. So it's easy to say things like, climate models don't do this, they should do it. But really pinpointing what they need to do, and how we can compare observations and models, I think is important.
Thank you both. It is tough when you're what you do is the explicit limitation everyone cites in their proposal to get money is that your global climate centers are bad at doing X, therefore we need Can I stick in a really quick follow-up just to Isabella, that for that boundary current process, what's the resolution required, do you think, to maybe accurately simulate that?
Yeah, I mean, Baylor's also a great person to ask for this, but you would need like at least a kilometer resolution, if not less than that. And yeah.
Kilometer scale or better.
Well, we can follow up more on that. That's a lot.
Yeah, that's not going to happen. So.
I mean, you do have shelf break currents at much coarser resolution than that. I guess I'm curious, but I've asked too many questions. But we'll see you in Delaware and follow up.
All right, up next we have Zinfen.
Oh, hi, Baylor. Thank you for for introducing the emulator, that kind of approach. I have a question about that. Maybe you actually mentioned that, but I didn't get it. The vacuum process included in that approach? I know you mentioned the diffusive process, but like the vertical upwelling, downwelling, those kind of processes included there?
Yeah, I mean, in some sense, the model that I was talking about is so simple that we don't really distinguish between advection and diffusion. It's just kind of anomalies at the surface end up at the bottom or at the top, and it's really just worrying about conservation of energy. I have talked some with Jonathan Gregory, who has an idea of how to make it more advective versus diffusive in nature, really distinguishing formation of water masses from an advective process and having different thoughts about how that should scale versus a diffusion. But there's sort of such a simple toy that they don't really mess with that distinction. The shocking part is that they do a pretty good job of explaining the changes that are observed once they are tuned. So I'm, there's not, in such a simple model, there's not a real distinction between advection and diffusion. There's just anomalies in one part of the ocean end up in a different part of the ocean later. And that's all it's really trying to capture with a very simple proportionality. When you're asking big scale questions, sometimes that's enough to answer it. Of course, if you're asking detailed questions about how much oxygen you get at the same time or how much carbon you get at the same time, you actually don't get a very good answer. There's a nice paper by Roland Safarian showing that if you try to do the carbon and energy cycle at the same time in this model, you can't do it. The downward propagation of carbon and downward propagation of energy are sufficiently different that they don't, you can't emulate them with the same model with the same parameters at all. You need kind of one model for one and one for the other.
Yeah, but I just have the feeling like because if assume it's a diffusive process, particularly consider in the future the surface gonna be warm first, right? So you're gonna have this temperature gradient. They're gonna always have a flux downward.
So that's true of this in general. Yes, the surface process is always working, but if you then reverse the sea surface, you're forcing changes and you're out of balance at the top, and then it's a flux upward. So it goes both ways because it does have a surface forcing as part of the system.
Okay, got it. Thank you. Oh, I have another question for Isabela. You mentioned I'm wondering for the oxygen measurement, can you look at one particular location? You mentioned in addition to the oxygen transported from the interior to the boundary, there could be something happening in local. I don't know whether you have the high enough vertical resolution measurement to see the vertical, basically time lag of the maximum for oxygen from surface to the bottom locally. Is that doable or?
It's so the instruments that we have are point measurements. So we don't have great vertical resolution. We're talking like several hundreds of meters between instruments. The OOI moorings do have some vertical profilers, which are really nice for looking at these kinds of questions. But near Greenland, we can't go anywhere near the surface because of sea ice and icebergs. So we're firstly limited to our top measurement being 50 meters if we're lucky. And then, yeah, we have big gaps. So we are forced to be creative and, think about things within these frameworks that we think we understand from the physics. But sort of do the best with what we have. The nice thing about oxygen is that you're pretty sure it has a clearer source in some ways than like TNS. The TNS gets pretty messy here because we have all sorts of different end members and they're all mixing up together. So the oxygen is really a nice tracer of the sort of surface to deep connection.
Yeah, I just feel like if in idealized case, you have like two measurements in vertical direction, a couple hundred meters away. If those kind of seasonal signal, you can do a lag correlation. Not sure whether that's kind of detectable.
Yeah. So there have been some versions of lag correlations sort of on seasonal timescales, and we do see this sort of 1 to 2 month connection between the interior and the boundary current at a couple different places. Yeah.
All right, thank you.
All right, up next we have Gail.
Hey, can you hear me? Yeah, hi. Yeah, hi everybody. So I guess it's a question maybe, first of all, I was going to ask, was there a recording of this? Because I missed the beginning. This? Excellent.
Yeah, it was recorded, yeah.
Excellent, thank you for that. My question is a bit, I guess, related to what Charlie was asking, but I'm thinking of the sort of the, the parameterization of the overflow that has been kind of an issue for decades. And more generally, I guess, about the simulation of bottom boundary currents, boundary conditions, whether they would be on the shelf or in the deep ocean or in the shelf break. So I guess the question is, kind of in terms of modeling and global modeling specifically, do we have kind of have we made progress on this? Do you have pointers as to what the best current solution would be to kind of have these things more or less properly resolved in a global model?
So I guess, well, I think that overflows are an entrainment process. That seems to be the biggest barrier to, and entrainment is very hard to resolve because you need the turbulence within the overflow as well as the overflow itself. So I think a direct approach is many decades away in terms of just directly resolving those. You could imagine an adaptive mesh or maybe a regional refinement mesh, but I think still you would probably want to, I didn't talk about emulators as parameterizations. I think you would probably emulate that and then put an emulated neural net of that overflow mixing into a system if you couldn't figure out an analytic way to do the entrainment parameterization itself. But I'm curious to hear Isabel's response.
Well, I can't say much about where the climate models are, but we're doing our best to measure those overflow waters, and I think if we can find, if we can somehow parameterize, this is what's happening at Denmark Strait, and this is what we see downstream. I think that would be a big step forward for the climate models without explicitly resolving it, finding out some. I heard sometimes there's like special tubes that the overflow waters can sort of get slid down, whatever it takes. But again, I think we should just have a reason to think that they're going to change in a certain way and that the response makes sense.
Yeah, I think observationally constrained simulations, I should have said, because for sure, the reason why we're better at the surface ocean and the reason why we're better at parameterizations in the atmosphere is because we can see them and have been observing them for a long time. Part of the difficulty with the deep ocean is that we don't have very many data to use to constrain those models at whatever resolution or parameterizations.
And that part is improving. Luckily, the subpolar North Atlantic is not that deep, so you don't even need the best of the best deep Argos. There's, Argo floats that go to 3,000 meters can get a lot of bang for your buck there.
Right. Thank you. I'm trying not to make like a tube myself in MIGDC, so that's partly why I'm asking. Thank you.
All right, up next we have Monique.
Hi, yeah, thank you. The two talks were really interesting. I had a question for Baylor about the emulator when you were talking about data assimilation and correcting for the mixed layer depths. Did I understand correctly that for data assimilation, that was just mixed layer depths at surface? And if yes, could you consider assimilating deep data? That's kind of related to what we were just talking about, but.
Yeah, sorry, I went very quickly through two different projects. One is really focused on mixed layer, just using it to constrain the model, and so the model parameters. And so that's imagine if you could fix the climate model so that their mixed layer depth was right. what would that do to the whole future projections out of those climate models? The data assimilation part is a separate question, and then we actually are using full depth ocean heat content reconstructions in our case, but those reconstructions are based on observations. So that is using surface observations, deep ocean observations, all together to give us what we think the deep ocean heat content is. So the data that's being assimilated is surface temperature, so air GSAT or GMST, whichever you prefer. We're not that careful to distinguish between them, at an annual mean, so to avoid effects of seasonality that we definitely couldn't get. And then the deep ocean heat content anomaly, which could be from Argo, or it could be from a reconstruction if you're going back before the days of Argo. And the nice thing about that system is that you actually get a running tally as to what the overall uncertainty was. So even when you have intermittent observations and things like that, if we didn't use a reconstruction, if we had used, say, International Geophysical Year observations or something, we would see how much that constrains the system or fails to. You're on the fly estimating the uncertainty of the observations as you go, or seeing that they're consistent with the amount of constraint they offer.
So you're saying that you can actually use the emulator and the assimilation to tell where we could need more data to make it better?
Yeah, or it's when you have new observations that show something special, how special are they? Are they special enough that the whole Earth's climate needs to be reinterpreted in terms of their anomaly effect, or are they within the range of what you expect, and so they're interesting regionally but not affecting global temperature or global statistics?
Okay. Are you using the OSNAP data, or is it possible, or is it too localized?
It's a little localized. Presumably OSNAP would eventually be in one of the OAC estimates that we would use, but I don't think it's in there yet. I'm pretty sure that RAPID and AMOC are in there, but that's an older system. So I think it's just we're waiting on the folks who are giving us the ocean heat content estimates to catch up. We're in discussions now on using multiple ocean heat content estimates as well as multiple surface temperature estimates in the system, because you can actually overload it with more data than you need and have it sort out among them which one to pay the most attention to. But that's a new project which we don't have written up yet.
Great, thanks.